You know, like, so it actually, that experience that actually counts. So how can we make the barrier smaller for learning, and how can we make you do less mistakes, and also, by consequence, make it less frustrating? You know, because it is frustrating when you try and make mistakes, or actually expensive, because if you're using a supercomputer center, those things are not cheap. You know, like you might be requesting, like I said before, like 1,000 nodes, and you should not. And then you're basically burning computer time that costs a lot of money in poorly using it, you know, like not getting anything reasonable. So we wanted to create something that would help you with that. The problem also we wanted to avoid is this, right? Garbage in, garbage out. We want to make sure that whatever you're doing, try to avoid that you make simple mistakes, that it's going to just create trash. Your simulation is going to be useless. It's not going to be something that you can publish. Okay, so the idea came up. So there was two of us, was myself and Theo. Theo is now a professor at the University of Regensburg in Germany. We were sharing an office, and we were discussing the whole time. And I remember we were discussing a lot with Chris Shipo in the back, like, how can we improve these things? And we came up with something like, so we should make something that should help you setting up MD simulations, offer both a simple and advanced interface, so that basically nearly everything you can do with them, you could do with it, and test the structures for missing loops, parameters, etc., and have a live view interface for testing and teaching, and include an interface for analysis of MD trajectories, at least for simple analysis. Okay. Then how it's going to look like? We came up with this design using, not developing the interface. Actually, this was actually created in CorelDRAW. We designed it, and like this is how it want to look like. And we had João at the time, another postdoc there. We were 3 postdocs. João, who is now at Moderna, that liked to had experience developing this type of interface, and like, okay, I can do it. So like the 3 of us actually discussed a lot, and 6 months later we had a prototype. You know? And that was fun because we did the stupid mistake of showing that to Klaus Schutten, who was the center leader at the time, this thing 2 weeks before a workshop like this. And of course, what happened? He made us prepare a version that the people in the workshop could do it. And it was a nightmare to make something that could actually work for like 50 people 2 weeks later. So, and João had a vacation schedule at the time. So he basically like had to cancel his vacations to work on it. And it was all crazy. But okay, so what we want to do, this is how an MD config file looks like. And this is the kind of thing that you're going to, if you're not familiar with MD, you're going to be familiar this week. You have to prepare a file that has all the information, like the structure. This is my structure file that has all the information of the connectivity of the atoms. You have another one that is a PDB that puts a position in the space for all those atoms. You're going to have to set a temperature the simulations are running. And then you're going to use that temperature to initiate your simulations. And you're going to have to set what are the files that you're going to have, like the velocities if you're restarting, or the coordinates if you're not restarting, or like what is your first step? Is it 0? Is like 50,000 because you're already restarting something. How many steps you want to run, and like so many others. You know, like the frequency you're going to write stuff, the output energy, the way you're going to calculate all the parameters. These are for parameters from the force field, the cutoffs, the switching, all of those things. And like I was saying, you see a lot of people just doing mistakes. You see, like when you get publications, we are reviewing it, we see like a lot of this thing, like, why are they doing that? Like, why are they using parameters that are for Ember in Charm, or vice versa? You know, like we see those things. So we need to make it easier. So like for instance, you're using Langevin for dynamics, you know, like, so this is how you use periodic boundary condition correctly, how you set all those things. And this is like all a part of this. So let's create, the idea was, okay, let's create the molecular dynamics as a molecular biophysics kit. You know, like if you're doing experimental work, a lot of the stuff that you do is from a kit, you know, like especially like molecular biology stuff, you know, like you want to make a mutation, use a quick change. You know, like you do something that there is a kit for that. You can do it without, like it's easier with a kit. So let's try to do the same kit idea for MD. So this kit is going to have, first thing, you're going to go to the Protein Data Bank. You're going to get the structure. You can have your own structure, by the way. You don't need to go to the PDB. You can have something that you solved the structure, or you get from AlphaFold. You can then select a chain molecule that you want to simulate, because a lot of the times there are more stuff than just the one you want to simulate. You can check that structure. And by check that structure, we mean, are there missing loops? Are there things there that we don't have parameters for? Like, we need to check for those. And you can visualize and check, show a nice representation, like Diego was showing today, you know, like make a nice representation that can help you to understand what is the system. Then you can come up with mutations, you know, like, because first, you might want to do mutation. Second, there might be mutations on the crystal structure that you're using that were mutated to make it easier to crystallize. Or like if you're crystallizing an enzyme, typically you have a mutation to stop the enzyme working. You know, like you want to make, so you want to reverse that mutation back. Also, you want to have something that allows you to change protonation state. And then for simulations, you need to solvate your system. You need to set the salt concentration. You need to select the protocols you want to do. You want to help with you all those steps. And then we're going to prepare all the files so that you have basically a folder with everything inside that you need to run. Okay? Now, after you have that folder, we want to give you 3 options. You can just click a button and run that simulation right there. You can run that simulation live. We had a button that allows you to visualize what's happening. You don't want to run like that for real, you know, because that slows down your simulation, but might be important if you're teaching someone, or if you want to see what is happening, why it is breaking, you know, like you can go there and watch it live. And I also give you the option to copy all those files to a supercomputer center and run it there. Now we want to also integrate that to Cyber Shuttle, that you just press a button and run it, I don't even know where. Because remember, like you can have 5 allocations on Cyber Shuttle, and Cyber Shuttle is going to decide for you what is the best place to run, because it's like, oh, the other one has less queue, let's put it there. And like, those things are things that we want for the future. Then you can do some live analysis if you're doing like running a simulation live, and then do some advanced analysis of the trajectory later. Not much advanced, like some, I would say, middle ground, but give you some analysis already integrated into it that's easier for you. Okay? This is how this thing looks like. So you have this easy tab at the end here, like the easy run, advanced run will give you more option, basic analysis, advanced analysis, and you load your structure and you can start playing with it. You're going to manipulate. First, you can go there and structure manipulation, and you can go there and change. I want to mutate this leucine to a threonine. So you want to change things, how they work. Or for instance, you want to change the protonation state of histidine. You want to change, you want to delete something. You want to add something. You want to check your structure for like, are there topology parameters missing? Are there things like all of that is being checked for you? If there is something missing, it's not going to let you do anything with it. If there is a gap in a loop, it's going to stop you from doing anything else, because if you just run it, it's going to connect the 2 points and it's going to just let that gap, like as if it does not exist, but it actually is missing residues. And if there's something that it cannot fix for you, like the gap, it's going to open, there's this info buttons that you see here at the top. It's going to open an info box. It's going to tell you, in this case, you need to do this, this, and that. Read these papers. You know, at least it's telling you what to do. You know, because some problems we cannot solve with an automated tool that easily. Like we could create something, but it's not. But at least let's guide you through the right process. Okay. Then you can check those simulations. You can do some simple analysis, like I said, and you can basically then follow what a protocol is typically on a simulation. So you can have the structure preparation, the structure alteration, right? Like the preparing your system, running, analyzing, you can have all of that easier for you. Another thing that is important is we tried as much as we could to not make this a black box. Okay. What do I mean by not, it's not a black box? I'm clicking buttons. Why is it not a black box? There are 2 things that we do that we hope help this to not be a black box. Number 1, everything that you clicked on, everything that you do there, when you hit like prepare, it's going to save a TCL file that is a script that redo everything you did. So like you can just go and open that script and look, oh, this is what it's being doing. This is what I'm doing. These are all the commands that VMD did for you, which you would do without QuickMD anyway. The other thing, it creates this text file that is like your method session of your paper, you know? We can improve now that with ChatGPT, right? But like basically it's giving you some initial text like, oh, I'm using Langevin dynamics, this citation. I'm using PME, this citation. I'm using this cutoff, this citation. Like I'm using this thing, citation. It's giving you all the information of the methodology that you're using. And you don't even have to worry about like, what is the paper that I need to cite if I'm using Charm 36, like it gives it to you, it's there. All this in the text file that you can basically copy and paste and adapt a little bit for your method section of your paper. Okay, so not so much a black box. You can actually see what it's doing. You can actually, when we created it, we were thinking that maybe you want to include that file in your as a supplementary information file. Other people can redo what you did. Helps you solve another problem, that is reproducibility. And QuickMD is going to be as fast as your computer can be. So when we publish this, so these are like, see, older, like 10-year-old software. Like this is the kind of thing that you could do. Of course, that those numbers are old. With today, can do much more, like I just showed you before. So if you have an A100 desktop, you can be running things at almost a microsecond per day, like roughly let's say most people run things around 100,000 atoms, so like 200 nanoseconds a day, maybe 400 if you're using hydrogen mass partitioning. Of course, this is the initial idea, like I mentioned. A lot of things that happened since then. João helped us a lot. Okay, now it's showing him the wrong affiliation. I forgot to move here. He passed through different places. He's now at Moderna. So we actually came up with interfaces for QMM simulation. So you can actually do hybrid QMM. It helps you to prepare what is the QM region, what is the MM region, visualize the orbitals, all of that. It has integration for molar factor, so you can design a ligand if you want, integrated that. Has automated force field parameter search using CGNFF. We also, like I said, you can visualize orbitals, like when you're analyzing. You can actually see, for instance, if you have a dynamics of the QM region, you can see things like the homolumo orbitals, how they oscillate over time, the energy, you can plot that. That's all integrated into QMD. And to give you an idea about the number of users, this is a survey we did 3 years ago. And these are like people, we asked VMD users what did they use to prepare their simulations. And remember, QuickMD is only used for NAMD and VMD is used for everything. So like I would say about 20–30% of VMD users are NAMD users. So a lot of them are saying they're using QuickMD. So we actually got a lot of people using it because like 85.5% of maybe like 20–30%, which is the total number of NAMD users. And this is 3 years ago, and we kept seeing more and more people using it. We are working now with VMD 2.0 on a QuickMD 2.0. There are a bunch of things we want to do, and Diego is working on that. So, for instance, we need a better way to prepare the structure. QuickFold is one of the answers for that we came up with already. You want to integrate that better into QuickMD and maybe remove QuickFold altogether, be part of QuickMD. That's the thing that I mentioned. That's Diego already showed better interface, but this is like kind of how it works. Like you can actually integrate to AlphaFold. I'm not going to show much of this because he already showed before. We also want to maybe better integration to homology modeling, to docking software, and maybe create a quick dock, maybe you want to do something for drug design, like Diego was saying, and integrate all of that. We also were thinking about today, if you're running an VMD, sorry, and you want to create a membrane, you can do that with QuickMD. You can create a membrane for you, but VMD can only create 2 types of membrane automatically. And like Emad has worked on developing a bunch of these membranes. Maybe we could integrate 50 membranes now, like we have those information. So we need to just bring that together into QuickMD 2.0 and help, like to use those things for your simulation. Also, automatic protonation stage detection. We don't do that now. There are a bunch of software for that. Maybe we can integrate one of them. Maybe we can work with people doing that. Include more advanced protocols. That is something that we have been working a lot. Maybe more free energy stuff. And rapid exchange, CoVars, white sampling, all those things. Prepare simulations for other MD software, or actually, another way of doing that is now NAMD3 is completely integrated. Like you can run Ember force field simulations the same way you're running Charm. So perhaps just include Ember force field here. Like you can just prepare a simulation for Ember force field through QuickMD. We need to do a better integration to NAMD 3.0, which does not exist at the moment. It's basically the same input, but like we can integrate better in take some advantage of that. And also, like Mariano, who was at the University of Illinois, he left, was working on revamping some of the analysis interface, integrate that better. And if you have any suggestions, bug Diego. You can bug me, but like Diego is the one actually doing that. And just want to say thank you. And like Quick Fold, by the way, is available for VMD 1.9.4. You don't need to alpha 50 something, that is the current one. So if you have any questions. Thank you. And yeah.
When you use QuickFold MD to prepare structures, can you predict pKa values and automatically protonate,
So
or you have to manually?
Yeah, you have to manually at the moment. We don't have an automated to integrate it to VMD. Like we don't develop any of those and we cannot distribute any of those. But like we might be able to quickly integrate something that you have to install yourself. Some of those.
So people generally use like pKa, make the prediction.
Exactly, and then just come here and change it. Yeah, that's another way of doing it. Or something that you know. You might know that a reaction can only happen if this